Good afternoon, and welcome to the Growing Together Conference 2020. Thanks for taking time. Thanks for being here. Welcome everyone in the live stream. It's a great pleasure to announce Thomas Zurbuchen this afternoon. The keynote of Thomas will be split into 3 legs. The first leg will be the presentation from Thomas about pushing boundaries through science and innovation. Then Thomas and I will sit down for a fireside chat next 20 minutes, and finally we will of course have questions from the audience here in the circle from you, and Thomas will be prepared to take the questions you might have. Thomas needs no introduction. Very quickly, he studied physics at the University of Bern. He moved on and became professor for physics and space engineering at the University of Michigan, where he also founded the Center for Entrepreneurship, a place where students learn how to do startups, and one of the biggest such programs in the United States today. And now, of course, he is the head of the science directorate at NASA. Thomas, thanks for taking time. Thanks for being here. Very looking forward to your talk.
Well, I'm so glad to be here today, and it's a huge honor to be also in the company D1. The first thing that really strikes me is how big it is. I remember the last time I was hanging out in the company, we all fit into a much smaller room in some restaurant somewhere. And the aspirations, of course, were always big. And I think that's what attracts me to this company. It's aspirations that are a little bit crazy. That's what attracts me to any project. Because frankly, one of the things I've learned, it's very hard to exceed expectations. So therefore, our expectations need to be huge. So it's better to be 90% close to a goal that is really far out than 100% of a goal that is modest. So that's what D1 has lived over the years, and that's what I want to talk about today. And what I want to do today is tell you a story. And what I'm going to do, of course, in the discussion, as we're looking at the questions and answers, we're going to generalize some of this, but I'm not going to do that or try that in this. I just want to tell you a story, and it's a story that has to do with the most complex space science mission ever done, a mission that will go into history as one of those times in which we look at the sky in a entirely new way. It's a history that, of course, started with the telescope, with Galileo looking out there in new ways, kind of at the sky and finding an enormous richness. Another part of that history is early in the 20th century, for the first time, with looking at observations from California in this case, it was discovered that there was not just one galaxy. There were many, many galaxies. In fact, the galaxies, of which we're in one part of, the Milky Way galaxy, those galaxies are all over, and the farther you looked in the universe, the faster these galaxies moved away from us. It almost felt, in 3 dimensions, like we were sitting on a balloon, kind of a 2-dimensional analog in which air was inflated in it and everything was increasing. So space itself was growing, space itself was expanding, and so was time. That was another big step. And another big step had to do with the Hubble Space Telescope. It turns out most of the light in the universe is not coming to Earth. You need to go to space to observe it, both the energetic universe. And what I'm going to talk to you about is part of the universe that we cannot look at because of the fact that it's not getting through the atmosphere. And we're going to talk about the infrared universe. So if you look at the infrared universe, suppose you were in space, of course your eyes would not see infrared. If you were really amplifying infrared, you would feel a ever so faint, kind of a sensation of a little bit of warmth. Now the only problem is that signals we're looking at are so far from the deep universe that that sensation of worth is minuscule. And so basically, what you need to do in that telescope is to achieve two things. First of all, we need to make it big, a big bucket of photons. So that photons that are coming from the deep universe, or even from nearby, are coming and are collected in a huge bucket. Only problem is when you go big with a telescope, it doesn't fit into a rocket. The biggest fairing, as of just a few days ago, that has ever been up in space, kind of the tip of a rocket, is just about 5 meters. What we need is more than 6 meters. Frankly, the bucket we want to be 6.5 meters in diameter. So like 3 people my size standing on top of each other in diameter. So that's number one, the bucket. By the way, if you fold the mirror, you need to put it back up and you need to put it in place so accurately that on a scale of the wavelength of the light, it basically, the wave does not know that there were multiple pieces. So pretty accurate. The second thing you need to do is you need to cool down the telescope so much that the signals of infrared from deep space are not overwhelmed by your own body heat, so to say. That means that you cannot do it at Earth. You need to go 1.5 million kilometers away from the Earth in a way, and it turns out there's this Lagrangian point, and 1.5 million kilometers kind of away from the Earth. If you wanted to look where that is, what you need to do is at midnight, look at the sky where the day before the sun was at noon. That's where the telescope is. So at midnight, all the way the opposite side of the sun. That's where the telescope is, 1.5 million kilometers. What you can do then is you can put up, if you want an umbrella, a sun shield, shield yourself from the sun and the Earth and the moon. The moon itself would be too warm to overwhelm the signal. By the way, that sun shield needs to be the size of a tennis court. And one of them is not good enough. You need 5 of those. And they need to be shaped exactly correctly mathematically. So radiation that comes in, if you want, gets killed to death as it tries to radiate forward. So it's the most complex telescope ever done. That's the story I want to tell you about. This is how the mirror looks. And the mirror is right here in the lab. And what I'm going to talk to you about is that as we're talking about the mission, you can think about technology. But most importantly, you should think about team. It turns out 70% to 80% of all problems you're going to solve with a big mission like this are people problems. Whether or not the vision, the goals, the objectives were understood not only by the leaders of the organization, all the way down to the people who touch that telescope, technicians that have no university education and frankly are the most important people in this particular case because they need to assemble this telescope. The question is, did they understand what needed to happen? It turned out we had huge problems because they did not understand. It's usually not because of them. I never blamed them. It's the middle management where some of this information goes and dies. And so basically, again, look at the technology, but think people, because the people are more important. So some of them are there. You see the reflection of the NASA logo in the mirror. You see the 18 pieces that are out there. And of course, each one of them has 7 actuators in the back that are minuscule, that need to all work together with another 20 actuators in the secondary mirror to together form the perfect telescope. We've never done that before. Here's the team, just a small fraction of the team. In fact, if I put everybody on that grassy area next to that one-to-one model, it would be 10,000 people approximately, from many different countries, including from Switzerland, by the way, from many different NASA centers, from many different states, from many different academic and university partners, and frankly, it took way too long. But you can learn kind of what happens. It's like running. if you want to do a marathon, I know some of you have, there's a good speed you need to hit. If you go too fast, you think it's 100 meters times a long, like you go too fast after a few kilometers, you're throwing up or you're not going to make it. Too fast is not good. But neither is too slow. We went too slow. You need to get the right stride. And frankly, I can tell you a lot if you want to know later about hitting that stride, especially after a time of crisis. How do you hit the stride? So you create rhythm. Rhythm, as every musician knows, is the most important thing of a music piece. The same is true in work. Hit the right rhythm, hit the right stride. There's a natural speed. It's just a little bit hard to get there, but you can do it without exhausting yourself. That's what you need to hit, because 27 years is no good. I spent, by the way, 2 hours on the phone yesterday. Think about the next telescope. What we're going to do there is we're going to put the schedule first. And we're going to put everything subordinate to the schedule, because we learned so much about the schedule being important. And none of us want to go through 27 years of hell again. Well, I want to tell you, I was in Christmas Day last year. I was in French Guiana. There were very few of us. Because of COVID, we tried very hard to get the rocket off. And it's one of those lucky coincidences, because of course, the people who built the rocket and built the telescope on the rocket are French citizens. The American team was there for 3 months down there to actually get the telescope ready. And remember, the value of that entire rocket as it stood there is $10 billion. It's a lot easier to calculate to Swiss francs that now than it used to be. But the point is $10 billion sitting on top of the rocket. Now, we went on Christmas Day. I want to just quickly talk about that. There had never been a Christmas Day where the French unionized workforce worked in this place. And by the way, that's correct. I actually am not advocating that we don't respect our holidays at all. There's time for the family and so forth, but they never worked. And the question is, we wanted to launch on the 24th, but the weather was not good. So kind of, if something went bad with the rocket, debris would have blown into town. And you know, you don't want to live in a place and pieces of metal and kerosene or kind of fuel come on you. You don't want to do that. So we had to delay to the next day. And the question was, are the French going to launch? And they said, yes. By the way, I never asked them, because I think they need to do that themselves, come at that conclusion. At the end, I walked around after a successful launch, and I thanked them and basically said, hey, I understand this was a huge sacrifice. Here's what they said, without any exception. They said, we did it for our American friends. They were with us for 3 months. We want them too to be able to celebrate Christmas with their families. For us, working that day enables that. To me, I couldn't come up with a better example of a good team. The French were becoming part of the team. By the way, we did that on purpose. When we shipped the telescope, we sat down, all the leaders, including Nobel Prize winners, and explained to them, because we learned so much about failing to do that before, about why the telescope was so important. And we told them about it. We excited them about this. And at the end, we became a team that exceeded in all dimensions. We were standing there on Christmas Day. By the way, I was really tired, because I could not sleep so well. Just like I was the rank highest NASA person there, so if something went badly, I'm the person giving the speech about $10 billion going into the ocean. And so for me, I practiced both of those speeches on camera the evening before, and it turns out, that's a good practice, but it doesn't help your sleep. So basically what we saw is this is the last picture of the telescope ever. By the way, the only reason that picture exists is because we asked Europeans to put a camera up there because we worried about the release of the telescope being right. They put it on in friendship, and it's of course, all the ad campaigns of Arianespace have that in there now. Because it's the most amazing thing. Just at the end, the solar panels came out, which is the goal of the day. It's basically meant we have power. the solar rays making the power of the telescope, and everybody in our entire row started crying because the telescope not only was off this planet, but it was out there as a spacecraft that worked. So what I'm going to do just before we start chatting about it, kind of tell you some of the amazing things we're looking at, and I'm going to start in the solar system and go out. So just give you a few things on the way. By the way, there's almost every week there's new pictures coming out. I just really hope you're following the right account so you see those pictures because they're mind-blowing. This, of course, is Jupiter. You immediately saw it. First of all, you learned in school Saturn has rings, Jupiter's doesn't. Wrong. There's rings right there. Jupiter has rings, by the way, so does Uranus. What happens if a moon dies or, collides with something. There's rings that are forming, and some of these rings are glowing in infrared because they have the particles that are rubbing against each other. What you immediately see, remember, you're looking at heat signals. Well, the polar regions are hot. What is that? Well, when you look at the polar regions, especially now at solar activity maximum, you see the northern lights. Perhaps you've seen them or in the south, same at Jupiter. What you can't see with your eyes is a huge magnetic field, like a dipole standing there, and energetic particles come from the top, rain down onto the polar regions, and they glow. Well, we knew that before, we thought, but here's the picture. And we can go measure how much it heats, and we can measure things that we never could before. So meet our celestial neighbor in a new light. We've never seen Jupiter that way before, and that's only the beginning. By the way, here's another planet. It's an exoplanet. It's a planet around another solar system, and in this case, the exoplanet is in our galaxy only 349 light years away. What you see is multiple colors of that. You see it's pretty crummy, the quality. Well, it's the first image in infrared ever of an exoplanet. And you see it's right at the hairy edge. The 2 hours I spent yesterday on the phone is to build a telescope which gets this picture-perfect quality of exoplanets. Of course, the trick is to find a picture of a firefly next to a beaming light that you have, for example, in a football stadium. So the star is really bright right next to it. So how do we blend it out? We have a coronagraph. It's like the way I'm blending you out with my thumb, right? That's what we're doing inside of the telescope. And we can do that. We're extremely excited about the exoplanet. The first time I saw pictures of this amazing world, the first images of this telescope I saw before they became public, I noticed that everybody was silent, and I looked around and I realized I'm not the only one fighting back tears. Because what we saw with this image is amazing. It's the Carina Nebula. It's telling you a story, of course, but what we saw is we saw that part of the universe, our own galaxy, for the first time ever, in a light that nobody had ever seen. And the Carina Nebula that is there with such beauty at 7,500 light years, of course, is an environment in which stars have gone through a full generation of evolution and have blown away their upper atmospheres and basically have seeded an environment in which new stars are forming. So each one of those dots in this kind of yellowish, brownish environment is a new star, just like our sun was, a few billion years ago, that is forming there with their own planets around it. What's exciting about this, the brownish stuff, we always, looking at UV, looking at visible light, we thought, well, they're atoms, atoms. Remember, you're full of star stuff. Every atom in your body is at least 1 billion years old. It's made by stars in the environment. What's on my rings, materials my wife gave me, and a family ring was done in converging neutron stars that exploded with a lot of energy. By the way, we only learned that a few years ago. We measured it for the first time. What's in this brown and yellow stuff are organic materials. A lot of carbon chains, alcohols, a lot of other carbon chains that are even more complex. When we went to school, remember, in the late 90s, we were sure that didn't exist because it's too complex. How could you do that? Multi-bodies, and you can do a good equation at the board. Not so fast. The world is much more beautiful. than we ever predict. That's what happens when you look at nature in a careful way. This is, of course, in the Eagle Nebula, the pillars of creation, another one of those areas. The one on the left has made history, from Hubble. On the right, you see the difference between looking at visible ultraviolet to infrared. First of all, you see all those dots in the back. Some of them are stars, the ones that have the patterns, the beams. That, of course, comes from the shape of the telescope. That makes that, right? If we can talk about spatial Fourier transforms, let's not, but that's what that is. All the other dots are galaxies. What we found are galaxies at numbers that, if we added them up, are more than every dust grain on all of Earth. More galaxies out there, each one of them at hundreds of billions of stars. And what you see from left to right is, because of the infrared, you see through that dust in many of the areas. And you see behind it. And frankly, if you focus on the dust, you see that there's a lot of dynamics that are happening. Stars that are trying to form and coalesce, while other bright stars next to it start trying to eat away those dust columns and trying to claim the matter for themselves. So this change that is out there in the sky is imaged. Stories are shown in ways we've never seen before. I never knew the movie It's a Wonderful Life. Perhaps you've seen it. It's a black and white movie. It's very popular in the US. But when the angel comes down in that Christmas movie, there's a constellation that is shown there. And it's Stephan's quintet, which is what I'm showing you here. Stephan's quintet, of course, are galaxies that are out there interacting with each other. Galaxies much farther away that are interacting with each other. And you see that brownish area again, driving star formation at the interfaces of galaxies. Yes, not only atoms interact with each other, create chemistry, stars interact with each other, create new energy, new metals, and so forth. Galaxies interact with each other at the largest scale. Everything changes all the time. And even though we think we look at the sky, it's always there the same way. It's just because we live too short a time. So for me, it's just a beautiful image of that. And the final image I want to talk about made news today. This is the first image, a deep exposure. Just a few hours, we looked deeply into the universe, and we looked into a place where we knew there's gravitational lensing. Do you see these brownish areas, it's almost like somebody dropped paint onto it? Well, what happened, there's a galactic cluster, something like 5 billion light years, and behind it, another few billion light years, are galaxies. And the light is trying to find the shortest way and is deflected because of the massive cluster, not only because of its real mass, because of its dark mass, dark matter that is there. And so what you're looking is another action shot in the universe that is showing basically how, at the largest scale, light is not going in straight lines, but is being, like Einstein predicted in Bern and in Zurich, like Einstein predicted, light is going around curves because gravity is bending space. What made news in this picture is that one of those orange dots, you look at that beam there just before it hits a galaxy in the foreground, there's a orange, reddish dot. One of them just broke the record for being the oldest galaxy ever observed, with 350 million years after the light years. Just to orient you, the universe is 13.8 billion years. So if you looked at this and you basically say, well, what this really is my storybook, because you, with all the atoms there, came from all the way from the beginning of the universe. And if you looked at the storybook and let's assume we're 50 years old, I'm 50 years old, well, I'm older than that, but 50 is easier to calculate than 54. So basically, if you looked at that and said, what is that a picture of? It's your 1-year-old self, the first image of that first generation galaxy in the universe we've never observed. The most exciting thing about this telescope is not what we have observed so far, it's what we're going to observe in the next 2-3 years. Everything we're observing today was motivated by what we didn't know before we put the telescope up. What gets the Nobel Prize or things we didn't know that we're now observing and motivating other observations. So what's really critical, whether it's in a company or whether it's in science, don't get stuck in a plan. Learn. Career planning is the same way, by the way. Don't make these linear career plans. That's crazy. You miss most of the fun. Figure out, learn, pivot, learn again, pivot, get better, get better, get better. And that's what, at the end, creates this amazing set of new thinking, new sense of awe of our sky. Every time I look at the sky now, I see something else I've never seen before. Not only do I see stars, I know there's galaxies. Not only we see that, something like 5 years ago, we learned that for each star, there's at least one planet out there. We did not know that. What we now learned is there are these old galaxies out there. We're observing for the first time the infrared universe like we've never seen. And of course, the way we did that is by putting people together that are different from each other, setting a truly ambitious and hard goal in front of them, and then learn faster than we failed. And that's how you get to something truly amazing. And with that, Simon, I'd like to invite you up and let's have a chat. Thank you so much.
Thanks so much, Thomas, for this wonderful presentation. It's a pleasure to listen to that. We can go on, we can skip the fireside chat. You mentioned 70% of the problems are people problems when you do technology, and I'm interested in that. So if you could go a little bit more into the how, and that's the purpose of what we're doing right now, right? Learn from you, try to figure out how you do what you do. If you could explain a bit how you come to winning teams, how you create winning teams.
So my observations have been, so I have something like 130 missions in my portfolio, right? And basically all of them are hard. And I just stand back and look at the problems that people bring me. And I just, frankly, I did not expect that. I expected that a lot of it will be technology things. We usually can do the technology. Like the right people in the room, we can solve the technology. But the people side is what we're struggling more with. So the kind of problems that you can have, the first one is kind of, I would call lack of thought diversity in the room. So the good news is, if you're all the same, like we have the same education, we're different, we know, but nonetheless, we have a lot the same. I know what you're going to say often before you say it because I've spent time with you. The good news is, when I'm hanging out with you and others like you, we agree really quickly on a path forward. But we have not considered many paths forward. So it's really important that other people are in a room who have other viewpoints and other thought processes that drive them. And the same is true in all dimensions. So lack of thought diversity creates really fast and decision making. Everybody's really proud and pats each other's shoulders. And what it really is glorified groupthink. And that happens at NASA, it happens at universities, it happens in companies, it happens everywhere. And we had a lot of that. I mean, I have to tell you, with web, I took the guy in a room and said, stop using adjectives. It's not excellent. It's not great. It's barely okay. So, but if you don't want to say barely okay, don't use adjectives. We're trying hard. Align kind of where you are, what you're understanding with what's actually happening, and let the people really help you. So kind of lack of that diversity of thought is a source of many problems. Another one has to do with really lack of understanding of vision. I think I mentioned that, right? Kind of, I want to tell you one mistake that happened here. We had built the whole telescope, and we were almost ready to start the testing. And there's this one guy who wanted to check electrical test of one of the engines that we're using to propel the telescope to where it is. And it's a cherry picker, so it's really big, right? We already said how high it is off the ground, so he's on a cherry picker, he's kind of there on his belly, goes in. And he basically said, you're supposed to apply 15 volts, is that correct? There's a second person who was supposed to check down whether or not it's 15 volts. He said, yeah, it's fine. Never checked. It was not 15, it was 30. He blew out the whole circuit. And so basically what happens, see, if you work on a $10 billion telescope, it's better to think than to act sometimes first, right? Actually check each other. And again, push each other. Did you do it right? Now, not all decisions are the same. Sometimes there's no penalty in mistakes. In this case, that penalty cost us close to $80 million because we had to wait and fix it every day cost $1 million. That was 80 days on the critical path. And there's a number of those. So kind of that understanding of what it means to build a $10 billion telescope needs to be understood all the way to the technician. We had to change everything bottoms up. We had to create kind of an open process in which people could deposit their worries. Nobody asked them ever for worries. And so we had to do that. That's another people problem, and I could go on and on for hours.
I understand. Many follow-up questions coming up here, but one is, you mentioned in other interviews that you listen to what is not being said. And I wonder how you do that. Do you make a list up front of topics you want to hear on and cross them off during the call, or how does this work? How do you detect the not discussed?
Yeah. So there's two things I do. First of all, I see presentation materials and I listen to the presenters. And I try to blend one or the other out. So I listen to what people are saying and imagining what they're saying. And then I turn off the sound, I look what they're showing. And if there's any discrepancy, there's BSing going on. And you need to go after it. Because, sometimes it's just a miss in kind of how something was done. Almost always something is hidden. So kind of at the discrepancies, you go find it, right? So you know somebody was putting dirt over a problem. So that's number one. The other one I do, kind of generally speaking, every mission that we're doing, and frankly, I've used it in company environments too, has to do with scope. What are we trying to do, how accurately? Has to do with cost, has to do with schedule, and there's 2-3 others, such variables. I don't know what they are in your business. But in your mind, create a matrix, and then you listen to which one is being discussed. And the one that's not being discussed is the one you want to jump on, because that's the gap. Like, they're missing something. Sometimes it's just a presentation issue, and you have to be ready for that. And sometimes, but more often than not, it's either a blind spot that they have, just rush over. It's like, wait, that is more interesting than what you're making it sound, or is truly, and it, usually I don't expect that you have that in your company. But what happens sometimes if you work with multiple companies, the incentives are such that under certain, because they have a quarterly earnings call or whatever, they're hiding problems from you. And I have no patience for that. Like, I literally have no patience. What I did is if you hide a problem from me, I make it so painful for you that you always want to tell me the problems first. Because when you tell me the problems first, I will never react. It's like, thank you so much for your openness. So what I had is all the senior VPs in the aerospace industry in which we're working are on my phone. If there's a problem anywhere in my missions, I get the text first, usually before the team tells me. And that's what I want, absolute honesty. See, it's really easy to not get bad news. I can tell you the recipe. First guy who gives you bad news, execute him. Like, scream at them, throw them out, fire them. Somebody who gives you bad news. It's very easy. You'll never get bad news again. But you also be blind to what's happening. So for me, it's that kind of brutal honesty is really one of the things I expect. I don't think we can do what we're doing if we're not brutally honest.
Sounds like trust is a very important concept for you.
Absolutely. And remember, trust is one of those horrible things. You can destroy it in 1 second, and it takes years to build. And so for me, it's kind of really recognizing that the key relationship here is a trust relationship. By the way, I use the same with government stakeholders. I remember the first time I gave an interview, I have a PR team. And he was a really good man, right? He worked with a previous, so somebody asked me, a journalist asked me, are you worried about webs? Like, absolutely. Like, don't say that, don't say that. It's like, well, but I am worried. I should be. Every reasonable person is worried because of the complexity and the challenges we've had, the history. And so kind of we had, close to 50% schedule efficiency. So for 1 day of work, we took 2 days. For a long time, I had to really reboot the system. I had to let a few people go, and we went to 95% schedule efficiency with all these changes that we're talking about within 3 months, and we stuck there. Brutal honesty, but really built that trust. Again, the company, I gave you the mistakes. One of the several mistakes they made, I never threw them under the bus in public. I gave them hell in my room. But in public, I always stood with them. I said, it's our team that failed, not company XYZ failed. Because at the end, we need to be successful as a team. So it's not useful to go blame them. I took a lot of flack internal to NASA. And at the end, of course, everybody's like, well, they're so motivated. Yeah, because I help, they saw I'm actually doing this for mission. I don't need to kind of, whip them. I don't feel better when I whip them. In public, let's be a team. Trust can be maintained even if you give bad news to people.
I quickly want to jump to stories because that sounds like a very important concept as well, creating compelling stories. And I remember that as a student, you helped Paul Wild, the famous astronomer at the University of Bern, taking pictures during the night from the sky, of course, because you wanted to learn astronomy, but also because Paul was such a great storyteller. So I wonder if a story stuck with you from that time.
Yeah. Well, of course, he's no longer with us, but yeah, I volunteered entirely because of the stories. I did not learn any astronomy that night or these nights, but he told me about all these stories. He knew Zwicky, the kind of amazing colleagues of Hubble, right, at Caltech. They hated each other. One of them had a cat on his lap, like you all did these kind of like, so he told me all these stories, and he talked about how dark the sky was, how he was observing, and Venus came above the horizon. He was frightened because it was suddenly so bright, because Venus itself brightened the whole telescope. So he told me all these stories just about how life was, but also how really the characteristics were of people like Zwicky, kind of the fearlessness that he had to kind of move astronomy forward and really transform it, right? He's the guy who first used dark matter as a concept. He didn't use the word, but he used it as a concept and so forth. So Paul Wild told me this. I never forgot the pillow fights in the dormitories, and some of them are Nobel Prize winners now. So so for me, I just love the man because of his stories.
So compelling stories seem to be a crucial tool in your work. Can you walk us through how you come up with an idea which ends up in a press conference? How you find the story, how you build it, how you bring it to life?
So usually I start with many stories, and then we take off the table until the best story.
They come to you while running?
Second?
They come to you while running?
Yeah, so they come to me while running, but also I really encourage others to tell stories in my teams. Tell us a story. Tell me something that excited you. It turns out stories are just really good vehicles to crystallize thought. Often story is much more powerful than you think. It's more than the sum of the words. Because see, what happens a story is more than just words or numbers. It's also emotion. It's a human connection. It's like, how do you interact with people? Listen to their stories, right? That's also why, everybody who grew up in Switzerland, right, or kind of in Europe, who learn different languages has so many advantages because they can reach into other cultural areas, right? I'll never forget sitting in Italy at a bar in a science meeting. On the other side of this was an old Italian man who only spoke Italian. Next to me was a Greek guy who only spoke English. And as we were talking, I figured out that this guy's grandpa this man, the bartender, attacked the village of this guy's grandpa. And so there was in World War II. And they had stories, and we were exchanging kind of how did it feel to attack? Like you can learn all the World War II histories and so forth. For me, Italy in the war will always be that grandpa. I will never forget that, how reluctant he said he was and how he felt terrible, and all his life he struggled with that, right? And that came out because of the fact that, and I suck at languages. I mean, my French teacher is no longer with us, would confirm that very much so.
I have tons of more questions, but I'm sure there are questions in the room. So let's switch over to
Please, let's do that.
Taking questions from the audience here at the circle.
Hi, thank you very much for the talk. It's been a pleasure. I was wondering if you could please comment on how you approach exploration versus exploitation in general in your project, because especially what you mentioned, I mean, someone makes a mistake, it's not exactly a few thousands that are ruined. So how do you choose to invest in a crazy idea but has a lot of potential, for example, versus utilize known technology in a new area, so forth?
It's a really profound question, and of course the answer is pretty lengthy, but let me just tell you, I deal with it the same way as with an investment portfolio. Like the only thing you do is invest in options or in vehicles that are attached to the stock market. The good news is you're really secure, like you're probably not losing your money, but you're also not winning any, right? So what you want to do is create an investment portfolio. When I went to NASA, that was the biggest challenge I felt we had. We were not, if you looked back at it, we were not worried enough about leadership. And because we were like, oh, we're the best. And I always told everybody the same story. It's Larry Page. I was in a room with Larry Page, and I'm sure you've heard the story, but I'll tell you again. Was in a room, he made a project decision. I just happened to be there as a consultant in that project, but he said something I'll never forget. He basically said, everybody thinks about leadership about some number. Like in his case, searches, percentage of people using Google versus another company, some number. Or how much money you get in your company. It's like, that's not leadership. It's the first derivative of that number. It's how fast that number changes. That's much more important than the number itself. If you're down here and you're on that slope, you're up here, you're on that slope. It's a matter of a few years, you're no longer the leader. So enduring leadership is much more focused on the gradient than it is there. So for me, what I did is created an investment portfolio that maybe actually declared that there's no launch we're doing without any new technologies on it. Because we don't want to just create kind of a good mission. We want to invest in kind of create more tools in a toolbox. So for me, you have to be able to also do that and be okay turning it down. You have kind of, when you take risks like that, every once in a while you have to say, look, it's not going to work. And it's fine, try again. Like, it's not, we're not able to do it, but try again. It's fine, we tried. That's the right thing to do. So for me, I really look at the mix of it, and I'm perfectly fine taking some crazy risk every once in a while. So we just did one. I don't know what you noticed. We launched a weather satellite, which is, we almost lost the damn satellite because the solar array didn't come out. But anyway, it was a software error we fixed, and it's all guys. So I had like 6 hours of hell. Like we thought we lost that. I thought it's easy, it's hard. It's always hard, right? But on top of that, we put a new simulator for a Mars entry vehicle. It's an inflatable heat shield that we dropped off in the Earth, and we dropped it back into the atmosphere. And we did it, kind of, it glows, right? Because it's an inflatable heat shield, 6 meters in diameter, and it went in front of Hawaii, went into the water. So we did that deliberately because we want to do that at Mars with humans. So we invest in that in a scalable model right there. So again, think of it as an investment portfolio. And never kind of stop investing it. There should always be some place you have going on when you're trying to get yourself. It's like finding a parking spot. Give yourself a chance to get lucky. Like, go look for the close parking spot if you're lazy like me. Go look, because if you're not looking, you're certainly not going to find it.
Thanks a lot, Thomas, for an inspirational speech. So my question is about the thing which I love about NASA the most, the fact that every current mission is a kind of a trampoline or a proving ground for something even more exciting. So 2 questions out of it. Is it an important planning part to have something tested out, like Ingenuity testing the interplanetary flight for something like Dragonfly on Titan and Hubble paving for Webb? And then, if this is a critical part, which is the future mission which you are the most excited about?
So yes, it's deliberate. So Ingenuity is a good example, right? By the way, I came to NASA. They were working on a helicopter. I had a meeting. They came to me and I basically said, tell me about this helicopter. How do you assess the risk? Somebody told me it's low risk. And I said, you're off the rover. Like on the spot, I kicked them off the rover. And I basically said, you need to earn your way back onto the rover, because if you don't realize it's high risk, you have now no chance of being successful. 0 chance. You need to be honest with it. Don't bullshit me. It's high risk. And so we did that. Now what happened, right? You may or may not have seen, we're doing Mars sample return. We're launching in 27, 28, and we just added 2 helicopters as reserve elements, and that's entirely because of the Ingenuity activity. We thought initially we could use it for that, but it was too big a leap. So basically what we did is a helicopter that can only take off 4 times. That was the requirement. I capped their money. I basically said it cannot be more than X million dollars. The simple reason for that, I wanted to protect them from bureaucracy and continuous improvement. It needs to make it as simple as possible, but it has to fly. By the way, as of this morning, it has flown 34 times. So it exceeded a little bit. But now with that technology, we use it for the next strategic mission. The same is true with this. The next mission that I'm most excited about, in terms of the discovery potential, is probably Mars sample return. We actually have new technologies on Perseverance that basically shows that what we have taken in from these sedimentary areas on Mars have a lot of organic inclusions. So of course we want to bring it here and see whether they're fossil life or not. So there's an honest to God chance that it is. Even if it's not, it's still interesting. But so kind of early in the 30s, we'll bring the samples back and give them to the best labs all over the world. Certainly they'll be in Zurich too.
Thank you.
Hi, Thomas. So the missions that you described take a long time, right? And you said that during the Webb mission, you learned a lot of stuff. How do you contain this knowledge? Is there, because I imagine sooner or later also you have to hand this over and you say for next mission you want to be more effective. How do you contain this knowledge? How do you document this? How do you, because it's such a big project, how do you make the next generation more successful?
It's actually a really profound question and one we're struggling with. Let me tell you what I did with Webb. So the moment we launched, I knew who the top 10 people were, the top thought leaders, and I basically went to them and said, you're working for me now. And basically I immediately pulled them up, and basically I meet them with every couple of weeks I meet them for several hours. And what we have been working on are lessons learned that they have, and we're turning them into training materials, but also are using the lessons learned to look at new options. We came up with entirely new architectures for next generation telescopes based on the lessons learned, because we need to really use different paradigms. So the question is, what are the paradigms that drove us in the wrong direction? And what are the paradigms that are opening now? So we're doing that. This is only one activity that I'm working on, and we're, again, turning it into training materials for earlier career leaders, right? What we've also done every once in a while, kind of after, so Perseverance was the first large-scale rover that launched on time, and it was really hard. I mean, when I came into NASA, it was orange, like we communicate, green is good, yellow is there's a problem, red is you have no chance, right? So we launched that orange turning red in the middle of COVID, right? But But so once we had launched, basically what we did is a broad activity, actually an independent review. It's like, what are the things we learned we should spread? So we've done on a number of occasions, both at the working level, but also at the leadership level, we've done these kind of learning things. Is it enough? My worry is that one of the mistakes we did on web, for example, we did not bring enough young people along. And I only noticed that too late. I was too late. The best way is to bring the next leader in the room where the hard decisions are made, and basically for them to learn where the issues are, and we missed that, I would argue. And so I'm trying to fix that. It's a problem we're struggling with. We create a lot of paperwork. Most of it is not useful because we don't think to go read it. So we're using a different set of things, but I'm not particularly confident that we're doing it great.
Okay. Well, thank you very much.
Yeah, thanks a lot. Maybe, so we do a lot with data, you know. So my question would be, how are you organizing your data? I guess you have a little bit of that.
Yeah, it's actually interesting. We're in the middle of a major reorganization. Next year, we declared as the year of open science. So what we're actually trying to do is move we had an open data policy for quite a while. NASA led that. The world in the meantime, with few exceptions, have followed. It's just more scientific return because of it. What we're really trying to do is do open science. So we actually want the algorithms out in the open as well, where it's GitHub or whatever the key mechanisms are. I want to do that, especially in earth science, because speed is of the essence when we look at some of the discoveries and so forth. So we're actually also moving most of the data from areas with zip code, right? When like you go get this data in the state of Michigan, that data in the state of, so we're moving it to the cloud. It's all natural, right? But sometimes you have to move it out. So what we're really trying to do is enable new ways of interrogation that the technologies that you're developing are actually really useful for AI, ML type of technologies, but also broad, just scalable technology. So we're literally in the process. We're investing this year close to $150 million of redoing this entire system. All the new earth science systems, we're starting in the new paradigm and we're pulling everything behind us. Earth science, by far, is the data leader in terms of just the sheer amount. So we're in the process of that. We're struggling still. A lot of it is still has to do with a lot of research happens at universities. People are still in the grad student downloads all the data and then massages it and writes a nice paper. It's just not very scalable in many areas. So what I've done is actually partnered with foundations that have themselves driven that paradigm, done workshops, brought in industry leaders, many of them from companies like Google, Facebook, Amazon, and others, right? And then really driven towards that. So it's a really interesting transformation that's happening right now. And the goal really is threefold: faster discovery. The second one is more openness of the data, more inclusion. What we're learning in our climate data, for example, is that the communities that need the data the most cannot get access to it, right? It took us usually in universities like a year of training in a tier 1 university for somebody to really be able to use the data the right way. And the third one is really to allow us to do research that otherwise could not be done by stringing together data sets, for example, over many decades, which is just really almost impossible right now in the previous paradigm. So we're there.
Hi, first of all, thank you for the fantastic talk and especially the images. They're amazing to see. And my question is regarding these images and the results that you've seen so far, because when you're working on a scientific experiment, you might have you have some theories that you're trying to prove or disprove, but then the most exciting thing is when you see something completely unexpected. So my question is, have you seen something like this? And if you have, what's the standout image or observation?
So it's still a little bit early to really answer that question well, just because we're, the time scale of discovery. Remember, the first time the data became public is the 14th of July. So frankly, there's a few hundred publications out there that are already there. Probably the biggest surprise is that we find many more early stage galaxies than we expected. But, so I had an argument with the theorists. They said, breaking the theories already. And they said, no, we can still squeeze it. So it's not enough anymore.
That's disappointing.
That it really breaks the theory, but it's early times, right? It's but for me, that I would say it's like, we saw all these publications came out of these early stage galaxies, but then we realized that every publication was about a different galaxy, which means there's many of them, of early stage candidates. And so anyway, that's one of them. Another one, has to do with some of these star-forming regions. It seems to be that the processes based only on one IR set of data, we had the wrong rates. It hasn't broken the theories massively yet. We're still fiddling with it. The theorists are still hopeful, but we'll see how it ends up. Without a doubt, it will break the theories. We have not pushed enough on it. We're just not good enough yet.
Hi, Thomas. Thank you so much for the talk. I don't know a lot about your field, but I understand that you've been working with SpaceX. There's some deals that were cut. I was wondering to what degree they have changed the way they operate, maybe also beyond the obvious of the reusable rockets.
So first of all, I work for the US government, right? And so for me, one of the biggest successes could be that there's an industry sector growing that wasn't there before. And that's what happened with SpaceX and the other companies. We have, basically it used to be that something like 30 years ago, all the rockets that we built were kind of government rockets. We had, we kept really tight. There's only one rocket right now that we're building, the one we just launched, by the way, 2 days, it was massive, holy cow. Anyways, I was like, and I never heard anything that loud during a launch, and I've seen many of them. But so that's the only one we've built kind of our own. So what SpaceX has done, not only did it create an opportunity for us to kind of move our technology expert elsewhere, it did two things. First of all, it reshored the technology, kind of the launch capability. It used to be that only 20% of the international launch market was American. It's now 85%. Of course, that's not good news for the Russians, and it's not good news for India. But the point is, SpaceX, you can go any week to Florida now. There's a launch. You don't need to plan anymore. So it's basically they just launched the 52nd rocket this year last week, right? So they did that. What also happened though, which is even more amazing, it probably cost the cost to go to space was cut. Even the time I was at NASA, 6 years or so, probably was cut 25%. So to get a kilogram to space costs 25% less. If Starship works, which is SpaceX, what they're trying to do, it goes from something that's closer to $10,000 to $100 per kilogram. So it's a 100x or 50x or so where we are right now improvement. So for me, it's great because I can use more money to do the science and less money for launch. I don't actually care about launch. It's just like the elevator in a building. Go up, right? So I mean, for me, that's how I want. And frankly, what I've done in many of the missions, I've actually allowed the investigators to buy launch themselves. I'm no longer managing at NASA. I'm trying to turn it over. So it's like if you wanted to get a private flight, with a little airplane, you go find a company that does that, sit in and go. So that's what we're trying to do, is it really change that paradigm. There's other sectors that I've started that are very different. For example, imaging the Earth. I worked on that problem with Google. In the meantime, there's multiple companies that image the Earth every day. Some of them with 5-meter resolution, some of them with 1.5-meter resolution. You saw when the Russians attacked Ukraine, the private sector put all these pictures out. It was not the US government, it's the private sector. So what we did at NASA, we said, hey, let's go buy these data. So we did. And frankly, what happened is, instead of us building the spacecraft, we're now using the data. And of course, what happens when you come up with an idea like that, everybody tells you it's impossible. They give you 10 reasons why it's no good. And basically what I did with my team is they asked me to cancel the investment in data buys. And eventually I got impatient. I smiled. But basically from now on, every time you ask me, I'm adding $1 million. So stop asking. It goes bigger and bigger. Okay, they said nobody will ever use these data. They're not well calibrated. As of last time I checked, there were 1,500 scientists across the United States that are using these data, commercial data, and doing amazing things, such as counting all the trees on Earth. That's an AI problem for you. It's really important because of course, that's where CO2 is stored. Kind of part of the CO2 equation is, where are plants growing, how many trees are there. So that is actually now addressed with these commercial data. I couldn't afford in an NASA paradigm doing that. So constantly we're looking at this. That sector, by the way, grew a lot because I basically said, every year, there's going to be money to buy data out there. So we're 6 companies we have under contract. There's another 3 under consideration. So we keep going.
I'm sure there are many more questions in the room, but I think we need to come to an end. Hey, Thomas, thanks so much for this inspiring talk, for sharing your experience with us and making time to be here. It was a great pleasure to have you here at the conference.
Thanks so much, and go D1. Thanks.